Welcome to the lecture series on numerical methods, a finite difference approach. In the last lecture, we have discussed explicit scheme and the implicit methods and their stability and convergences. And in the present lecture, we will discuss about this stability of Crank-Nicoloson scheme with both these methods like matrix method and Newman's method. So, whenever we are just going for this Crank-Nicoloson scheme, especially if you will just consider these equations that is in the form of like del u by del t, this equals to del square u by del x square, then we can just obtain this discretized scheme as in the form of like minus r u I minus 1 j plus 1 plus 2 into 1 plus r u I j plus 1 minus r u I plus 1 j plus 1, this equals to r u I minus 1 j plus 2 into 1 minus r u I j plus r u I plus 1 j. So, if you will just consider like u as the true solution and u star is an approximated solution that I have just discussed in the last lecture, and if we can just take the differences like u minus u star, so that will just give you this error terms here. Especially as I have told you that if you will just consider this coefficients that is in the form of like minus r u I minus 1 j plus 1 plus 2 into 1 plus r u I j plus 1 minus r u I plus 1 j plus 1, this equals to r u I minus 1 j plus 2 into 1 minus r u I j plus r u I plus 1 j here. And if you will just consider this approximated solution that is in the form of like u star here, and if you will just take the difference from this earlier equation that is in the form of like u minus u star in each of these coefficients, and that is just signified as e here, and each of these coefficients that will be remained in that position there. So, then we can just write this error terms as in the form of like minus r e p minus 1 q plus 1 plus 2 into 1 plus r e p q plus 1 minus r e p plus 1 q plus 1, this equals to r e p minus 1 q 2 into 1 minus r e p q plus r e p plus 1 q here. Since we have just replaced here p in terms of like I and q in terms of j here, so that is why these error terms are represented in this form here. So, if you will just express this complete system of equations, that is if this p will vary from like I equals to 1 to n minus 1 and j will vary from 1 to n minus 1 there, then we can have a n minus 1 system of equations, and we can just formulate a matrix that is of order like n minus 1 cross n minus 1 here. So, if you just express this one in matrix form, then we can just write it as p u e q plus 1, since if you just see here, so this q plus 1 coefficients remains same in each of the terms on the left hand side. So, that is why we can just express this complete coefficients that is in the form of p here, and this coefficients that is in the form of e q plus 1, but especially we can just signify that one as like e 1 like 1 e q plus 1 e 2 q plus 1 up to e q plus 1 q plus 1 there. So, that is why if we can just express this one in a separated form, that we want to keep this variable in the left hand side only and all of this matrix into the right hand side, then we can just write this complete system as p inverse q into u q here. So, if you just see here this coefficients of p that can be written as like 2 into 1 plus r minus r 0. If you will just see here that these coefficients, especially these equations are represented as in the form of minus r e p minus 1 q plus 1 plus 2 1 plus r e p q plus 1 minus r e p plus 1 q plus 1, this equals to r e p minus 1 q plus 2 into 1 minus r e p q plus R E P plus 1 Q here. And if you will just compatible form, if you will just write here, so first term this will just take this value from the boundary condition itself, and it is especially 0, as I have discussed in the last lecture. Since these boundary conditions are fixed along these boundaries and which cannot be changed with the solution process, so that's why this error is always 0 along the boundaries. So that's why this first term it will just take the 0 value there itself. And if you will just put the first coefficient here, that is nothing but the first coefficient will be p here. So if you will start from 1 here, then we can just write first coefficient as 0. So that's why this first coefficient will come over here as 2 into 1 plus r, and second coefficient as minus r here, and third itself it will start as a 0 here itself. And similarly, if you just write all the terms, then in the last term we can just write this one as like minus r 2 into 1 plus r here. And this coefficients, it can be multiplied, that is in the form of like E1 q plus 1, like E2 q plus 2, so likewise it will just go. So sorry, this is a q plus 1 here, so all remains constant. So especially if you will just see here, since a q plus 1 is fixed at each of the terms, so that's why we are just writing this one as q plus 1 here. And if you will just write this right hand side terms, you can just find that first point, if you will just see p equals to 1, this will also take this boundary condition here. So that's why this coefficient will be 0. So the starting coefficient, it will just come in the form of like here as a 2 into 1 minus r here. And next coefficient, you can just see that this will just come as r here, and rest of these elements as 0 here. And immediate next element, if you will just see, that will just come as r 2 into 1 minus r, so likewise it will just continue, and in the final term we can just get it as like r 2 into 1 minus r here. And the coefficient, if you will just see, this can be written in the form of, since q is fixed here, we can just write this one as like E1 q, E2 q up to E of n minus 1 q, if you will just write this one. So in the final form, if you will just see, this equation just takes this form like E of q plus 1 t, this equals to E1 q plus 1, E2 q plus 1 up to E of n minus 1 q plus 1 there. So that's why this is just forming a system of matrix or a system of equations which can be transformed to a matrix that is in the order of n minus 1 into n minus 1 here. And if you just see this right hand side term, that is nothing but E1 q, as I have explained, E2 q up to En minus 1 q here. And if we will just write this one as in the form of like, since our matrix is written as in the form of like EQ plus 1, this equals to P inverse Q EQ here. So that is EQ plus 1, that is nothing but P inverse Q EQ here. And for stability, we already have discussed in the implicit approach that we should have to write this P inverse Q as in the matrix form, since always we will if you will have like distinct eigenvalues, then we can just write it in a linear combination form there, and each of these eigenvalues, it can be represented like A into Vs, as we have written these vectors as a Vs there. So A Vs equals to lambda S Vs there, and in each of this multiplication of matrices, it can be transformed to lambda square, lambda q, likewise it can just go up to lambda to the power n minus 1. And that's why if you will just take this stability of these schemes, then we can just write this one as the multiplication, since here this matrix is formed as there itself we have just written in terms of A, that's why I am just writing this one as A here. A is nothing but P inverse Q for this system of equations here. And if we will just write for this stability of this scheme here, so then we can just write lambda into P inverse Q, it should be less or equal to 1. And to get this formulation in a generalized form, if you will just see here, so then in each of these coefficients, if you will just visualize here, P is associated these terms like So P is associated these terms like P equals to, it is defined as a 2 into 1 plus R minus R 0. Second term, if you just see, it is minus R 2 into 1 plus R minus R 0, rest of the terms we are just considering. So likewise, the last term, it is just coming as minus R 2 into 1 plus R here. And similarly, if you just see here, so Q term, it is also involving these terms like 2 into 1 minus R 0, and then next term R 2 into 1 minus R, it is just continued. So likewise, last term, it is just written as R 2 into 1 minus R. So if you just take this diagonal elements here, so each of this R coefficient that involves a multiplier term as 2 there, and the immediate next term, if you just see, this also contains like minus 1, so likewise it is just going. So that's why we want to write this R coefficients in a separate matrix form, and here we have defined that coefficients as in the form of T here. So that's why if you just see here, R coefficient that is just taking 2 here, then this minus R coefficient that is minus 1 here. Again, if you just see the second row, this is just taken as minus 1, then 2 minus 1. So likewise we have just written as the T as a matrix here. So if you will just write this E of Q plus 1 as in the form of, since we have just written this matrix that is in the form of like P inverse Q, then we can just formulate that one as, since T is the matrix which takes the coefficients of R there itself, so it can be written in the form of RT here. And the rest of these elements, if you just see, that just take these coefficients, that it is just expressed in the form of like 2 at the diagonal positions there itself. So we can just express that one as a 2 into a identity matrix there. So that's why this complete system, it can be written in the form of like 2I plus RT inverse, since we are just writing there that as like P inverse into Q there. So that's why these diagonal elements only we are just representing here. So directly it can take this as in the inverse form here, that as a 2I plus RT whole inverse, and 2I minus RT into EQ here. So if you can just see this one clearly, it can be signified from this matrix sense if you just see both these matrices here. So if we want to find this eigenvalues of this matrix, so especially we have to signify this as a complete matrix form here, then we can just subtract the lambda values from each of these diagonal elements there itself. So to do this one, so if you just assume that S is a matrix which is defined is in the form of like 2I plus RT whole inverse into 2I minus RT, that is nothing but P inverse Q here. So we can just obtain this eigenvalues if we can just write it in a determinant form. So if suppose mu is the eigenvalue of T and lambda is the eigenvalue of S here, then this relationship between T and S can be written as like lambda equals to 2 minus mu R by 2 plus mu R. Since if you just see here this above system here, we are just writing here S as the system, that is nothing but P inverse Q. And if you will just consider here 2, since 2I means this is just taking 2 into all of these eigenvalues, sorry, identity matrix there. So that's why in each of these diagonal entries, if you just subtract this minus lambda, so it can be represented as minus 2 lambda up to the last value as minus 2 lambda there. And if you just see this other coefficient here, that can be written as like RT term. RT term means if you just see, this is also taking this elements that is in the form of like a diagonal elements, tri-diagonal elements, just it is just taking the coefficients. So that's why it can be written in the form of like 2 minus mu R, since we are just writing this inverse terms there, and that's why it can just take to the down here. So that's why this is just written as a 2 plus mu R, since mu is the eigenvalue associated with a T value here, and in the upper side we can just write this is 2I minus RT. So that's why, so T coefficient that is just replaced by this mu here. So that's why this eigenvalue of S can be represented in the form of 2 minus mu r by 2 plus mu r. And for stability, already we have known that we have to consider that absolute value of lambda, it should be less or equal to 1. So if you just consider this lambda should be less or equal to 1 here, then we have this inequality like lambda, this is less or equal to 2 minus mu r by 2 plus mu r here. So that's why we are just writing this one as in the form of like lambda should be less or equal to, if you just consider both the sides there itself. So since it is just considered as 1 here, so we can just write this absolute value, it is also less than 1 there. So if we are just writing in this form there, then we can just write this one as minus 1, it should be less or equal to 2 minus mu r by 2 plus mu r, this should be less or equal to 1 there, and which gives the value like mu minus 2, it should be lies between minus 2 and 2 there. Since mu is greater than 0, if you will just use Bright's theorem, that is especially applicable for this spectral radius that takes the largest eigenvalue in magnitude sense. So that's why we are just considering this mu, it should be lies between 0 and 4 there. And if you just continue this calculation, then we can just find that lambda equals to 2 minus mu r by 2 plus mu r for mu lies between 0 and 4. And especially we can just visualize that if modulus of lambda is less than 2 minus mu r by 2 plus mu r, so then we can just consider modulus of lambda value is always less than 1 whenever we will just consider this any positive value of r equals to del t by del x square. Hence Crank-Nicoloson scheme is stable for all values of r, that is nothing but it is unconditionally stable. Especially if you will just go for like our earlier discussion, you can just find that explicit scheme, whatever it is just applicable, it is just stable whenever your r value is less than half, and we have just explained that explained by considering one example that if we are just considering like explicit scheme for this problem like del u by del t equals to del square u by del x square. So after certain step, it is just showing some unrealistic physical behavior. So that's why it is best to use like Crank-Nicoloson scheme instead of explicit scheme, since explicit scheme puts some restriction that it can be applicable whenever you will have this r should be less than half. But this does not have any restriction for Crank-Nicoloson scheme. So that's why we can just move with any type of like del x or del t condition to deal this differential equation, partial differential equations. So alternatively, we can also show that if we can just find directly these eigenvalues by using this Bright's-Fike theorem or like Grest-Gorin theorem. So we can just obtain this eigenvalue that is in the form of like 4 sine square by s pi by 2n. Even if for that condition, if you will just check this lambda s value, so that will just come as like 1 minus 2 r sine square s pi by 2n by 1 plus 2 r sine square s pi by 2n, since it is just defined in the form of like 1 minus 2 r mu by 1 plus 2 r mu there. So obviously if you will just consider this lambda s is less than 1 for all positive values, so we can just get this condition also. If you will just go for like Newman's method here, so Newman's method already we have discussed that we have to consider this error coefficients as in the form of e to the power alpha q del t into e to the power I beta p delta x. And if you will just put this one in the error formulation, since our coefficients it is just taking in the form of like minus r. So if you will just see our earlier formulation, you can just visualize that these coefficients are taking is in the form of like minus r e p minus 1 q plus 1 plus 2 into 1 plus r e p q plus 1 minus r e p plus 1 q plus 1. This is just taken as like r e p minus 1 q plus 2 into 1 minus r e p q plus r e p plus 1 q here. And if you just put all these coefficient terms here, that can be written in the form of, since minus r is present there, so minus r it can be written, and e of p minus 1 q plus 1. So directly if you just put these values here, it can be written in the form of like e to the power. So some manipulation in the last lecture we have done, and finally we have just obtained that one as e to the power minus I beta delta x e to the power alpha del t. Since some of these coefficients we can just take from this left hand side and some of the coefficients from the right hand side as the r coefficients, and it can just get cancelled it out. So that's why this complete formulation it is just taking as e to the power minus I beta delta x e to the power alpha del t for this e of p minus 1 q plus 1 term. And if you will just take this term for like e of p q plus 1, so it is just taking in the form of like e to the power alpha del t here. And similarly, if you will just take this coefficient for e of p plus 1 q plus 1 after cancelling this left hand side coefficients and right hand side coefficients, sum of the coefficients of r, then this term will be reduced to e to the power I beta delta x. Similarly, the same coefficients you can just visualize in the right hand side also. And especially if you will just write it in a compact form, then we can just take common e to the power alpha del t in the left hand side, and it can be written in the form of like 2 plus 2r minus 2r cos beta delta x. This equals to 2 minus 2r plus 2r cos beta delta x here. Since already you have known that cos x, it can be written in the form of like e to the power x plus e to the power minus x by 2. So that's why it is just represented in this form here. If we can just express these terms as in the form of e to the power alpha del t as like 1 minus r plus r cos beta delta x divided by 1 plus r minus r cos beta delta x, since 2 both sides it can be taken common and it can be cancelled it out. So this can be written as like 1 minus 2r sin square beta delta x by 2 by 1 plus 2r sin square beta delta x by 2. Especially if you will just see here, so usually cos x it is just written in the form of like e to the power ix plus e to the power minus ix by 2 here. So this just clarifies the sense that whenever we are just expressing this e to the power ix, it is also written as cos x plus I sin x, and in that form you can just write e to the power minus ix, that is cos x minus I sin x. So from there itself directly if you just add it up, then you can just obtain this formula. So if we will just go for this further movement of this Newman's method, we can just consider the stability condition, that is nothing but modulus of e to the power alpha del t, it should be less or equal to 1, which is true for all values of r greater or equal to 0 here. Since we are just considering here e to the power alpha del t, that is nothing but, if you just see, that is nothing but absolute value of this one here. And if this is less than 1, which is true for all values of r greater or equal to 0, since if you just consider this condition, that is in the form of like 1 minus 2r square sin square beta delta x by 2, it should be lies between 0 and 1 there itself. Hence in fully implicit scheme, it is always we can just say that it is unconditionally stable here. Thank you for listening this lecture.